Hi there, fourth graders. This week we're talking about equivalent fractions, and we're going to learn a couple different ways you can use to find equivalent fractions or to determine if two fractions are equivalent to one another. For this activity, for this lesson, you need a piece of paper or two, because you're going to do a bit of drawing, and pencil, and you need two colors. They can be two different crayons or two different markers or highlighters or colored pencils, but you need two different colors. So paper and pencil and two colors. Pause the video now, go get those, and come back. So the first thing we need to do is we need to understand what equivalence or equivalent means. Two fractions are equivalent if they represent the same portion of the same whole. Let me give you an example. If I had two candy bars, I had a king size Snickers, you know, the really big ones that you can get if you go to the awesome houses on Halloween. Not my house, I give out the small stuff, whatever. So a king size Snickers bar, and I have a fun size Snickers bar. That means I've got two Snickers bars, and one of them is real big, king size. And the other one is fun size. Now, I don't understand that title because I think that the smaller candy bar is less fun, but that's just my opinion. So if I have a king size Snickers bar like this one here, and I have a fun size Snickers bar like this one here, and I tell you, you get to have half of both, would you be getting the same amount of Snickers bar out of both of them? Like if I said you're getting half of the king size Snickers bar, is that the same thing as half of the fun size Snickers bar? It's not. Actually, this is a whole lot less. So half of a king size and half of a fun size are not equivalent because they're two fractions that don't represent the same portion of the same whole. The whole is different. This is a much bigger whole than this whole is. So you might have seen before things like 1/2 equals 1/2. Those things are equivalent, but that's only true if we're talking about the same whole or the same candy bar or the same original shape. Let's look at some examples that are showing us some visual models of equivalence. If you don't have this jotted down though, you should pause because you definitely need this definition written down, and I think we need to note that these are not equivalent. So pause now, draw the picture, write the definition, show the non-example, and then move on to the next slide. Okay, so here I have two circles. They're the exact same circle. I know that they are because I drew this circle first, and then I copied and pasted it. So I know they're exactly the same. And I have shaded 1/4 of this circle right here. 1/4. Okay? Then I shaded 1/4 of this circle. Because the circles are the same, they are the same whole, check, and the same amount is shaded, check. These are equivalent fractions. They're the same. Make sure you have that. Okay, now I have another set of fractions. I know that my whole is the same because, again, I copied and pasted. And I can look at them and I can say they're the same rectangle. So first I shaded in 2/4 of the first rectangle. And then I shaded in just 1/2 of the second rectangle. Now, when I look at those and I eyeball it, this amount right here is the same shaded amount as this part right here. In fact, if the technology would allow me, I could cut this piece out and move it over on top of that piece and see that they're exactly the same. So in this case, 2/4 is equivalent to 1/2 because it's the same whole and the same shaded amount. Even though this is 2 pieces and this is only 1 piece, it's still equivalent because this piece is twice as big as this piece. It's the same as 2 of them. Jot that down. Here's another example. Well, let's look. Do I have the same whole? That's my first question I have to ask. This rectangle and that rectangle, yep, they're the same, okay? Now, same shaded amount. Well, I've got 1, 2, 3 up here. And I have 1, 2, 3, 4, 5, 6 down here. But I can see that this portion that I've got right here is exactly the same as this portion. So that makes them equivalent. It's the same whole. It's partitioned differently, but the same amount of the whole rectangle is shaded. So those are equivalent. Now here's another one. I've got a circle. It's the exact same circle as this one over here. This one, I have 1/3 shaded. And this one over here, I've got 2/6 shaded. We can see that this piece right here is exactly the same as this piece right here. So they are equivalent. Now I do want to show you something. I want to say, what's the best way for me to do this? Nope. No. Let's imagine that, here, I'll just do it this way. Let's imagine that I've got my 2 circles. Definitely the same circle because you watched me copy and paste it, right? If I partitioned this one, let's do it this way. Let's say this is 1/4 here. 2/4. Okay. And let's say that I partition this one not into 4ths, but instead into 1/8. Now I'm doing a quick sketch. It's not going to be perfect because I'm trying to do it quickly for you. And let's say that I shade 1/4, 1/8, 2/8, 3/8, 4/8. Okay, so I've got 2/4 over here, and I have 4/8 over here. The question is, are these equivalent? Well, it's the same circle, so first question is answered. Same whole. Perfect. Great. Now let's look. This is this much. Is this the same, even though it's on the other side of the circle? If I flipped it over and bloop, plopped it on there, would it be the same? It would. So I know that in all of these examples, they were in the exact same spots, right? Like it was 1, 2, 3, 1, 2, 3. And then over here, it's here, and it's in the exact same spot. Even when it's not in the exact same spot, it's a different part of the circle, they're still equivalent because it's the same shape. The same amount of the circle is what's shaded. All right, let's look at some non-examples. Oops, I should go back. These are definitely equivalent. Okay. So these ones aren't equivalent. Now, they both represent 1/2. Pause for a second and ask yourself, why aren't they equivalent then? How is 1/2 not equal to 1/2? Well, we have 2 questions we ask ourselves. Same whole and same shade. Let's look. Are they the same whole? This is kind of like that king size, fun size, right? Oops. king size, fun size. This 1/2 is a lot bigger than this 1/2. That's why they're not equivalent, because they're not from the same original shape or the same whole. Okay, let's look at these. 2 questions, same whole, same amount. Okay, let's look. Same rectangle, so that's right. Is the same amount shaded? Well, over here I've got 1, 2, 3, 4. And over here I have 1, 2, 3, 4, 5. This one has a piece that the other one doesn't have, doesn't it? So they are not equivalent. So they can't be considered equivalent. So we can find equivalent fractions using a variety of methods. One is using visual models. That's what we've done here. These are all visual models that either represent or don't represent equivalent fractions. Okay? Another way is using number lines. And lastly, it's using multiplying and dividing. Before I move on to using, we're going to practice equivalent models one more time. Let's go forward and then I'll come back if I need to. So a couple more with visual models. So the question is, are these equivalent? Is the blue equivalent to the red? Well, first I need to figure out what fraction do I have here? Well, I've got 2 parts total, so that's my denominator. One of them is red. Okay? And over here, I've got 1, 2, 3, 4, 5, 6, 7, 8 parts total. 3 of them are shaded. So now I'm going to ask myself, is this shaded portion the same amount shaded as this? And I look at it and I say, no, it's definitely not. It's the same whole, but it is not the same portion shaded. So these are not equivalent. My answer here is no. Okay, how about these ones? Are they equivalent? Well, they're both rectangles, but are they the same size rectangle? Are they the same whole? I don't think that they are. But they do have the same amount shaded, sort of, right? Like, it's the same shape. This kind of upside down L shape, it looks like. But this one's smaller than that one because the whole is originally smaller. So these are not equivalent. Even though this one is 6/8 and this one is 3/4. Because they're not the same whole to begin with, they cannot be equivalent fractions. How about these ones? Well, this one represents, let's see, what do I have? 1, 2, 3, 4, 5, 6, 7, 8. So this is 16ths. And this one looks like it's 8ths. Okay? So I have 1, 2, 3, 4, 5, 6 16ths and 3/8. Well, it's the same whole. I can tell looking at it. Those are the same rectangle. Is the amount that's shaded equivalent? If I was able to cut this out and place it on top of here, would it match up perfectly? I think it would. So yes, these are equivalent. We can say they are equivalent. Now we can also use number lines. You guys learned in 3rd grade that you can label a fraction on a number line by counting the number of total partitions, not lines. So this is 1, 2, 3, 4. So the denominator's 4, and I'm on the 3rd jump. So that one's 3/4. 1, 2, 3, 4, 5, 6, 7, 8 is the denominator, and I am on the 6th jump. When I look at my number lines and I notice that these are lined up exactly together, that makes them equivalent. So 3/4 on this number line is equivalent to 6/8 on this number line. And the reason is because this whole is the same thing as this whole. They are the same number line. You can tell because the zeros line up and the 1s line up. So those are equivalent. Awesome. Let's look at these. I got to plot 2/3. Okay, so that means I've got to break this into thirds. I learned a trick that if the denominator is 3, I have to draw 2 lines. It's always 2 less lines than the denominator. So let's see if I can do it. That's pretty close. So this is 1, 2, 3. So that's right. Okay, thirds. And I need 2 of them. So that's here. Okay. And now I'm going to do eighths. I got to break this one into eighths. Okay. I'm going to test it. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's eighths. Okay, 4/8. 1, 2, 3, 4. So I can see these ones are not equivalent because they do not line up when I stack my number lines. So in this case, no. 2/3 is not equivalent to 4/8. And actually, in no case are they. They're never equivalent. Okay, the last method to use is multiplying and dividing. And I'm going to tell you what. This is the easiest one and the fastest one, but only if you know your multiplication and division facts. So Miss Harrison and Miss Zimmerman and I have been kind of harping on you guys all year about how important these multiplication and division facts are, and this is one of the many reasons why. So if you multiply both the numerator and the denominator by the same thing, you have made an equivalent fraction. Let me show you what I mean by that. But before I do, pause and write that down. Okay. If I start out with the fraction 2/3, if I multiply the top and the bottom by the exact same thing, and I get the right answers because I know my multiplication facts, 2 times 3 is 6, 3 times 3 is 9, then these are equivalent fractions. Piece of cake. So if I had 2/3, for example, let's say I multiplied both the numerator and the denominator by 4. I would end up with the new fraction 8/12, because 2 times 4 is 8, 3 times 4 is 12. Those are equivalent fractions. Let's look at another one. It also works with division. If I start with 5/10, if I divide both the top and the bottom by 5, 5 divided by 5 is 1, 10 divided by 5 is 2, I've made an equivalent fraction. I could also multiply. If I had 5/10, let's say I multiplied by 8. 5 times 8 is 40. 10 times 8 is 80. Because both of them are multiplied by 8, these are equivalent. So there's an infinite number of equivalent fractions when you multiply and divide. Now here's a non-example. In looking at it, you can already see why. The top is multiplied by 4, and the bottom is multiplied by 2. These have to be the same. If they're not the same, then you're not getting an equivalent fraction. You're just getting a random fraction. 1 times 4 is 4, 3 times 2 is 6. These two things aren't the same. And I can prove it. Let's see if it lets me do this. Nope. Ooh. Yes. Okay. I can prove it. Watch. If I draw a rectangle, and I duplicate it so that it's exactly the same, and I know it's exactly the same, and I cut the first one into thirds, and the second one into sixths, and shade them to match, if I have 1/3 is that the same thing as 4/6? No, they're the same whole, but they're certainly not the same amount shaded. So they cannot be equivalent. Now, if I started with 1/3 and I actually multiplied both of them by 4, what would I get? 1 times 4 is 4. 3 times 4 is 12. Those two are equivalent. I could use the 2. 1/3 multiply times 2 times 2. 1 times 2 is 2. 3 times 2 is 6. Those are equivalent. However, these are not, because you did 2 different multipliers. The multipliers or the divisors must be the same. Say it after me. The multipliers and the divisors must be the same. Here's an example. 7 divided by 7 is 1. 21 divided by 7 is 3. So yes, these are equivalent. They have the same divisor. These ones, on the other hand, are not the same. 5 divided by 5 is 1. That's true. 8 divided by 2 is 4. That's true. But because these two things aren't the same thing, the fractions are no longer equivalent. Okay, let's find some ones that are actually equivalent. 1/2 is equivalent to, let's see, 3/6. 1 times 3 is 6. 2 times 3, 1 times 3 is 3, and 2 times 3 is 6. So that's a good example. Okay, let's check this one. 1 times 8 is 8. 2 times what is 18? It's not 8, it's 9. That does not work. How about 2/4? 1 times 2 is 2, and 2 times 2 is 4. Are these the same? Then yes, that's equivalent. Let's look at 5/9. 1 times 5 is 5. 2 times nothing is 9. So that's not right. Okay, let's do another one. Let's go over here. 1 times 4 is 4. 2 times nothing is 7. That doesn't work. 1 times 6 is 6. 2 times 6 is 12. That one works. So 3/6, 2/4, and 6/12. Those are all equivalent to 1/2. However, 4/7, 5/10, and 8/18, they're not. Do you see how I looked at the fraction and I kind of created for myself? I looked at it like this in my mind, I guess. I said, okay, what multiplication sentence would this be? One times what is 3? 1 times 3 is 3. 2 times what is 6? 2 times 3 is 6. Since these are the same, it's equivalent. Then, when I was looking at some of the others, 1/2 and 4/10, for example. So I do the same thing. 1 times what equals 4? 4. 2 times what equals 10? 5. Are these the same? No. Then this is not equivalent. Okay, let's look at this one. I want you to pause. I want you to test these out, and then I want you to come back here, unpause, and check your work, and I'll have the right ones marked for you. So here's what I determined while you were working. 2/3 is equivalent to 4/6, which is also equivalent to 6/9. It's also equivalent to 14 21sts, and it is also equivalent to 16 24ths. Okay, one more time. Pause, see which ones work, come back and check your answer. And there you have it. I found 4 again. 3/5 works. That time I divided. I used a division because 6 divided by 2 is 3 and 10 divided by 2 is 5. I got 60 100ths was equivalent. I've got 12 20ths is equivalent, and 30 50ths is equivalent. Because this one is divided by 2 and 2, times 10 and 10, times 2 and 2, times 5 and 5. Okay, so you're going to go forward. If you missed any of the notes on any of these slides, I recommend that you pause, rewind, go back, get the notes, reach out to me if you need some help on this. I have some open office hours this afternoon. So check the connection tab. You're welcome to come to those. I have some office hours that are specific for small groups, and if you were invited to those, that's in your connection tab. But even if you weren't invited to math small groups, there's one open slot today that you could come to, anybody. So I'm opening that one up to anybody who wants extra help with this practice. Anybody else who wants practice with this skill. So I hope to see some of you there. Reach out to me if you need anything.